Our first goal is to get this computer program to do the analysis more than once. Ultimately, we want to change the standard deviation each time it does this analysis. But for now, let's just figure out how to create these things called loops in computer programs. Computers excel at doing the same calculation over and over again, so just about every programming language out there has some sort of loop programmatic structure to it. In this case, we're going to create a loop that surrounds this code. Basically, we want to repeat the process of adding a realization of the synthetic error. We want to do the linear regression on that new realization of the synthetic error, and we want to extract the results of that particular realization. Typically, when you're writing a computer program, you're going to write the code that does what you want it to do once, and then start putting loops around the things that it needs to do many times. And that's what we've done here. So if we want to start a loop, I'm going to make some room for some more code before this statement right here. And we're going to use what's called a for loop. The idea of a for loop is it keeps going through some number of lines of code until the computer reaches some condition that tells it to stop. The way that you program a for loop in R is you create a new variable, and you say that that variable should take on the value of every element of a vector and each element of the vector defines one time through the loop. The syntax for this is to start with a for command, and it's going to turn blue because that's a keyword in R. So our RStudio text editor is going to recognize that keyword and turn it blue for us. And then in parentheses, you're going to have a variable name. I'm going to call that variable index. It'll become clearer later why I call it index, but let's just call the variable that we have iterate or that take on each value of the vector that we define. We'll call that an index. Then you need another keyword, the word in. So I'm saying index in, and then you give the name of the vector that you want that to be in. So let's say we want to try 3 different standard deviations ultimately. And that way, and for that reason, I need to have a vector that has 3 elements in it to get it to go through this loop 3 times. Well, a simple way to create a vector with 3 elements is use the colon operator. Remember, this creates a vector of integers that takes on every value between the starting value and the end value if they're integers. So if we use 1 colon 3, this will be a vector with 3 values. Each value will be a 1, 2, and 3 in the 3 elements of that vector. After the closed parentheses, after you've defined the variable and the vector that says that has the elements that that variable will take on, then we need the curly brackets to specify a block of code. So everything inside these curly brackets is going to be the code that runs inside our loop. Now we already have the code that we want inside our loop down here. So I'm going to delete this curly bracket and put it down here at the bottom of our loop. As you'll often see with curly brackets that separate a particular code that's running in a loop, and also if you're defining functions, which we'll talk about later, it's generally good form to take all of the code that's between the curly brackets and indent it by 1 tab. So in this case, we're going to indent all of this, and this just makes it a lot easier to see where things like loops start and end as you're reading through the code. And this is pretty true for just about every programming language in terms of the style of indenting all of the lines of code that are within a given loop. So now we have the code that will run this 3 times. And indeed, it ran it 3 times, but it really didn't do anything each of those 3 times. It did the same thing every time, as a matter of fact, because nothing changed. The standard deviation was the same each time, so we need to do something about that. To get a different standard deviation each time through the loop, as you might imagine, we have to tell the computer before the loop what those standard deviations should be. In this case, we're going through the loop 3 times, so we're going to need a vector with 3 values in it, specifying the 3 different standard deviations we want to use in our analysis. And that has to happen before the loop starts. So I'm going to add some more space before our loop here, And I'm going to add a new vector that I'm going to call SDS for SDs, plural of SD. And I'm just going to use the C function to quickly create a vector of 3 values that we're going to try. And I'm going to choose the values 0.1, 0.5, and 1. So ultimately, I now have a vector with 3 values in it, 0.1, 0.5, and 1, and these are the values that we want the standard deviation to take on each time through the loop, because we're going to change our approximation of the error each time through. So what do I have to change this to? Well, I obviously can't use that 2, otherwise I'll just use the 2 every time. Well, I can refer back to SDS as the name of the vector, but I just want one of the values from this vector. And this is where the logic of using the term index comes back in. I knew that I was going to use the counter that's counting 1 through 3 each time through this loop as an index later on. In this case, I'm using an index of an existing vector to index that vector to get the value that I want each time through the loop. So the first time through this loop, index will have the value of 1. Therefore, the first time through the loop, my SD will take on the value of the first element of this vector. After it completes the loop once, it'll start over. The second time through, index will have the value 2. Therefore, this value will have the second element of this vector, and etc. Third element, and that's the last time through this loop. We now have a loop that runs 3 times, and each time it runs with a different standard deviation when it's coming up with a realization of the error for the dependent variable. However, we're not really storing any results of these different analyses, so we don't really know what's going on each time through. So there's more that we need to do in order to keep track of whatever is interesting is happening each time through the loop. In this case, what we really want is the standard error in the slope estimate that is coming from this linear regression and the summary statistics of the linear regression each time through. Now, when it comes to loops, it's always most efficient to create the vector of the size that you need and then fill that vector in as you go through your loop. In R, it will let you take a vector and increase the size of the vector by 1 every time through the loop. And if you have a very short loop like this, it probably isn't going to matter. The problem is once you get to a loop that has 10,000 elements, then it is very much going to matter because it is very inefficient to constantly be remaking a vector of a different size each time through the loop. If you make a vector of the right size once and then fill in those values, that code will run much faster than code where you are adding to a vector each time through. So we'll get into more detail about how that works later. But for now, let's go ahead and create another vector. And again, we have to do this before the loop starts because we want to make the vector so we can fill it in as it goes. We're going to call this standard errors, or STDERRS. So this is going to hold the standard errors for each time through the loop, or the standard error in the slope for each time through the loop. Now this is going to need to be the same size as the SDS vector because we're going to run through the loop 3 times and we'll get a standard error each time. When you are creating this space or this vector for things to add later, you also want to make sure you don't put numbers in it. Because if you put numbers in it and then there's a bug in your later code that doesn't replace those numbers, you may think those numbers are real, and it's really hard to spot whether those numbers got replaced or not. So sometimes you'll see code that will put zeros in by default. I much prefer to put in what are called NAs, or not availables. That makes sure that any math that I try to do with this vector later is going to result in an NA if I have not populated that element of the vector. And that's what I want to happen. I don't want to put a 0 in there because zeros are real numbers. And I don't want to do math with them by mistake. So one quick way to put NAs is to use the rep function, or the repeat function. We're going to repeat the same value a multiple number of times. And in this case, we want numeric non-availables. To make a numeric non-available, I can do an as.numeric, or an as numeric. That just forces whatever I send to as numeric to be numeric. And I'm going to send it an NA. And that's keyword in R. So capital NA is a keyword. You'll see it show up in blue in your editor. And there's a times argument that lets me repeat the same thing multiple times using the rep function. In this case, I want that to be 3 because there are 3 standard deviations, and I'll have 3 standard errors corresponding to those. Now that I have my data structure set up, I can fill it in, but I want to do that inside the loop. So each time through the loop, I want to fill in one of the elements of this standard errors vector with the standard error corresponding to that time through the loop. And I'll need to do that after this LM summary line because the value that I want to put in the standard errors is part of this summary. So what I need here is stderrs. And as with before, I will need to index it. I need to say this time through the loop with this particular index, I want you to fill that element of this vector with the number that's coming out of this analysis. So I can assign to the element of that vector the LM summary. I'm going to use the $ because remember LM summary is a list. I want to get the coefficients out of that LM summary. And remember that coefficients is a matrix, a matrix with names for the rows and columns. The rows are the different parameters that you're estimating in linear regression. I need to use an x if I want the slope, because that's the name of my independent variable. And the name of the column is capital STD period space ERROR. And the space and the capitalizations are really important. It is case sensitive. It has to match exactly. So now each time through the loop, I'm collecting a standard error, and it's going in the appropriate index for each time through the loop, and it's going to take on the value of the standard error in the slope coming out of that coefficients matrix. Let's go ahead and run this. And if everything's working right, if we look at that standard errors vector, I'll have 3 different standard errors corresponding to the 3 different standard deviations that I used for randomly selecting my error. We're now running this 3 times. We're getting a different standard deviation as the input each time and getting a different standard error in the slope as the output each time in these 2 different vectors. Let's plot them against each other. That seems like an easy way to take a look at how the value of the standard deviation propagates through into the standard error in the slope. This also sounds a lot like the exercise that I've asked you to do in the homework. So we're going to use some simple plotting commands here. I need to go ahead and start up a device to use. In this case, I'm going to use Windows since I'm working on a Windows machine. You want to use Quartz. If you are using a Mac, I'm going to give it a width of height of 8 and a height of 6. That should give us a easily visible aspect ratio. And then I'm simply going to plot as my x variable or my abscissa, I'm going to plot my SDS. And as my ordinate or my y-axis, I'm going to plot STDERRS or standard errors. So I will see the standard error in my slope versus the standard deviation that I used in order to create this synthetic error. Now, just to make sure I know what I'm looking at, I'm going to go ahead and label the axes. So in plot, you can do that using the xlab argument, or the xlabel argument, xlab. And I'm going to say this is the standard deviation of artificial error. Don't forget the commas. And my y label is going to be my standard error in estimate of slope. So let's run this and we'll see what pops up. And we see we have 3 values, one at 1, one at 0.5, and one at 0.1. Those are the 3 values we chose for our standard deviations. And we get values somewhere less than 0.01, somewhere around 0.03, and somewhere a little over 0.06 for the standard errors in the slope. So as you might expect when you're propagating error, any uncertainty in your observations going into this regression analysis are going to show up as uncertainty in the parameters of the statistical analysis.